discussed how the current can be generated in a semiconductor material which has been doped by group 3 or group 5 impurity atoms. So the mechanism by which the charge is transferred based on whether it's the electrons or the holes. We have two types of currents in semiconductors. So one is the drift and the other is the diffusion currents. And this, if the name implies, you can understand the drift is due to the applied E fields in a semiconductor. Okay. Whereas the diffusion current is more concerned with it has to do with the concentration of the dopings. Okay, I mean, if in a region you have highly concentrated impurity atoms which are contributing more electrons, for example, a group 5 phosphorus doping has been done, and the concentration is higher in a certain region, then from high region to low region, you will have a transfer of charge. Okay, and owing to this transfer of charge, you will have a small diffusion currents in a semiconductor. So these are two processes by which the currents are generated. Now, we have already described in the previous videos the creation of negatively charged electrons and positively charged holes in the semiconductor. If these charged particles move, you see a current is generated. Now, these charged electrons and holes are simply referred to as the carriers. Okay, so the current can either be due to the negatively charged particles. For example, if it is an N-type material, you are doping your semiconductor with group 5 elements, you have excess of negatively charged particles, electrons in this case, so it's an N-type material, so you have the electrons as the majority carriers. Okay, if it is boron doped, group 3 doped silicon crystal, then you have holes because boron is going to accept the electrons from the nearby valence electrons, and it's going to create holes. Okay, so you have a majority of holes if it is group 3 doped, and the holes are the majority carriers for p-type. Okay, so both of the electron and holes, they constitute the conduction of current in semiconductors. So the two basic processes which cause the electron and holes to move in semiconductor are the drift, which is the movement caused by the electric field, and then you have the diffusion, which is the flow caused by the variation in the concentration, that is concentration gradients. Well, these concentration gradients, they could occur due to inhomogeneous, non-homogeneous doping distributions, okay, or by the injection of quantity of electrons or holes, more holes into one region, okay, in a certain region, and then there is a certain, let's say, a gradient in the concentration of charges, and then from more concentrated region to less concentrated region, there is a diffusion of charges which can constitute the diffusion current. Okay. Now, so to understand the drift current density, let's assume that we have an electric field which is applied to a semiconductor, and this field produces a force naturally that acts on free electrons and holes. So they in turn then experience a net drift velocity and the net movement. So you see in these figures 1.8, I have an N-type semiconductor in part A, and then I have a P-type semiconductor in part B. And the direction of field is as such, you can assume that we have the charge distribution. For example, the semiconductor could be placed in a, let's say, between two charged capacitor plates. The E field direction is as such, okay? So it's from positive to negative. Similarly, we can have the same direction of the field. E field is as such, okay, dot, 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 dot. So you can see the E field is from positive to negatively charged plate. And what happens in an N-type material, semiconductor material, we have the majority of free carriers, those are electrons, okay, and they are free to move in the conduction band of the lattice. So due to the opposing charge of the electron, they are going to experience a force that is opposite to that of the E field. Okay, the E field is directed towards right, but due to the opposing charge, the electron is going to experience force towards the positive plate, okay, towards this direction. So this is the drift velocity of the charges, and the drift current density, which is given in terms of amps per centimeter square. You see, conventionally, the conventional current, if you recall, is taken as opposite to the flow of charges, opposite flow of electrons. So the conventional current density can be taken in the same direction as that of the E field. And the same goes for the hole carriers, the positive carriers, okay? Because the holes are positively charged and they are going to experience the force in the same direction as that of E field, okay? So the idea is that if you apply an E field, depending on whether it is P-type or N-type, if it is N-type, the electron is going to experience the force in the opposite directions, holes are going to experience the force in another direction, which is directed in the direction of E field. But the current densities, the drift current densities are the same, directed in the same direction as E field, at the applied E field. Okay, so the direction of the applied E fields are shown, and the resulting carrier drift velocities and the drift current densities for N-type and P-type semiconductors are shown over here. You see the conventional current direction are as such that the drift currents in both N-type and P-type are the same due to electrons or holes as the E field is applied, as in the direction of E field. Okay. Now, if you consider N-type semiconductor with a large number of free electrons, you see whenever an E field is applied, they're going to experience a force, right? So when E field is applied in one direction, it produces a force on the electrons in the opposite direction, and because of the electron's negative charge, you have the drift velocity which is opposing. So the direction of this drift velocity is negative with respect to the E field, okay, because of the negative charge of the electron. The electron is going to experience force towards the positive plate, okay, and this drift velocity is a very strong function of the applied electric field. Okay, more E field is applied, more force that is going to be experienced by the charge, and these are related by a constant mu n, which is the mobility of the free charge carrier in the N-type semiconductor. Okay, so the drift velocity is in terms of centimeters per second, which can be written in, as such by this relationship. This negative sign is indicating the direction of force of the charges, which is opposing the E field, and mu n is the constant called the electron mobility. Okay. And electron mobility has to do with the concentration of the charges, okay, how much and not how much concentration of charges are there. So it has to do with the mobility. It has units of centimeter square per volt seconds, okay. And for a very low doped silicon, the value of mu n is typically about 1350 centimeter square volt second, and this value you will see is typically more than twice that of a whole mobility. The electron mobility is much higher, is more than twice that of whole mobility, and the mobility can be thought of as a parameter indicating how well an electron can move in a semiconductor lattice, right? So one thing is evident, that the drift and the force that is being experienced by the charge carriers in N-type or P-type semiconductor is due to the applied electric field, and the drift velocity, the strong function, is a linear function of electric field. And this is true for very small electric fields. You see, if you go on increasing electric field, you might have a phenomenon known as drift velocity saturation, and then you cannot go on increasing electric field to increase the drift velocity. The drift current is not going to increase. Okay, so the negative, the only difference between the N-type and P-type semiconductor drift velocities is due to the direction of the drift velocity because of the charge, because of the opposing charge. So the negative sign in the top equation is for the N-type material, indicates that the electron drift velocity is opposing to that of the applied electric field, as shown in figure 1.8a. Okay. Now, the electron drift produces a drift current density, which is in terms of amps per centimeter square, that is current per unit area. And you see this current density, of course, if the charges which are experiencing force in an E field are having a certain drift velocity, then you have to multiply this with the concentration, how much charges are there in, let's say, unit cubic centimeter, and then this E is the magnitude of the charge, 1.6 10 to the power minus 9 coulombs, fundamental charge of the electron. Okay, so if you multiply the fundamental charge of electron, multiply the number of electrons, now that gives you sort of how much charge which is being moved due to the applied electric field. Okay, so multiplication of these three quantity gives you the drift current density. And if you substitute this for the velocity, which is a function of a linear function of the applied electric field, we have this relationship. Okay, and this relationship is the current density due to the negatively charged carriers, majority carriers in an n-type semiconductor material. Okay, so this N is the electron concentration in per cubic centimeter. E in this context is the magnitude of the electronic charge. So the conventional drift current is opposing the direction from the flow of negative charge, which means that the drift current in an n-type semiconductor is the same as the direction of the applied electric field. So the conventional current, since it is it opposes the flow of charges, the drift current is in the same direction of E field. Okay, in both cases, in both for n-type and p-type, the drift current density has the same direction as the applied electric field. Okay, because the conventional current drift opposes the flow of negatively charged electrons. So you have the drift current direction the same as the applied electric field. Okay. So next, consider a p-type semiconductor with a large number of holes, as in figure 1.8b. So same situation applies over here. You see that the drift velocity of the holes due to the applied electric field, again it's a linear relationship with the applied electric field, but this time the mobility is mu p, okay, with a positive sign. So electric field is applied in one direction, produces a force on the holes in the same direction because of the positive charge on the holes. So the holes acquire a drift velocity in centimeters per second, which can be written as such, and this hole mobility again has the same units as we had earlier for n-type material. But the low-doped silicon has a typical value of 480 centimeters square, which is less than half of the value of electron mobility. So electrons are more mobile for a typically low-doped silicon, same material. This is one thing to notice, that although applied electric field does, for small electric field, if you go on increasing small electric field, you have more drift velocities, and as compared to holes, electrons are more mobile. Okay, they can contribute to the conductivity of the material more than the holes. Okay, so the positive sign in the above equation indicates that the drift velocity is in the same direction as the applied electric field. That goes for the hole, and the hole drift produces a drift current density, which is given by this relation. Well, this is the same relation. All you have to do is you have to bring the concentration of the holes. P is the concentration of hole per cubic centimeter. E is the fundamental charge over here. And then if you expand this for V, which is the drift velocity for the holes, you bring this relationship over here. Expand this. Okay, you will have a very similar current density relationship in terms of amps per centimeter squares, and you will see that for a typical for a small electric field, you can have a current of few hundred amps per centimeters through a very low doped silicon material. Okay, whether it's n-type or p-type doesn't matter. So but this small electric field is capable enough to produce a current of few hundred amps per centimeter square, a current density of 100 amps per centimeter squares. So okay, again E is the magnitude of the electronic charge in these relationships. The conventional drift current is in the same direction as the flow of positive charge, which means that the drift current in a p-type material is also in the same direction as the applied electric field, which we have already said before. So you see, the only difference is that the drift velocities are different because of the charge, because of the negative charge of the electron and the positive charge on the hole. But the conventional drift current direction is in the same direction as the applied E field for both n-type and p-type semiconductors. Okay. Now, since the semiconductor contains both electron and holes, the total drift current density can be formulated by considering the sum of both electron and hole components. So you bring both the current densities to both holes and both the majority carriers and the minority carriers in a typical semiconductor material is going to consist of holes and electrons, which are going to contribute towards the conduction of current. So the total drift current density is then written as such, and you see over here for the applied electric field, so the same with the applied electric field and the same charge. Well, you can take E out, and this factor what you are left with over here, okay, this factor is known as the conductivity of the material, which is you can say a function of the concentration of charges holes, and then you have the concentration of negatively charged particles, which are the electrons, and then you have those mobilities. Okay, and these mobilities again are owing to secondary effects. These are dependent on the concentration of charges. All right. So conductivity, you can say it depends on the concentration of charges, number one, and then it also depends on the mobility of charges. So that's the conductivity. And what you can see over here is you have the current density, which comes out as a linear relationship, with that of the applied electric field, and this conductivity is related to the resistivity of the material rho. And one way to look at this equation is that of as an Ohm's law, that if your voltage is applied to a semiconductor, then it results in the conduction of current due to both holes and electrons, and that contribute towards the conduction of current, and their mobilities and concentrations are what are contributing to the conductivity of the material. Okay, so sigma formally is the conductivity of a semiconductor in ohm centimeters inverse, and resistivity, and rho is the resistivity of the semiconductor, which is the inverse of conductivity of the material. So the conductivity is related to the concentration of electron and holes again. Now, if the electric field is the result of applying voltage to the semiconductor, then the above equation becomes a linear relationship between the current and voltage, and is one of the Ohm's law. Okay, it's one of the Ohm's law that applied for an applied voltage, you have a current, and this voltage and current are linearly related to the resistance of the material. Okay, how much the material is going to resist to the flow of charges. But over here, the flow of charges are being constituted by both the holes and electrons separately with their separate mobilities and concentrations. So from the above equation again, we see that the conductivity can be changed from a strongly N-type material which has large number of electrons by introducing donor impurity, doping to a strongly P-type semiconductor material which has more holes, by acceptor impurity doping. So being able to control the conductivity of a semiconductor by selective doping is what enables us to fabricate a variety of electronic devices that are available. Now, this example gives you an idea how to calculate the drift current density for a given semiconductor. So as an example, if you consider a piece of a silicon at room temperature 300 kelvins doped with arsenic, so we have a donor impurity. So arsenic means that it's an N-type material, so majority carriers are electrons. Okay, so we don't need to even consider the mobility or the conduction due to the positive charge carriers, because they are in minority, right? The concentration is very small in magnitude compared to that of the electrons. So the concentration of this arsenic atom is given as, and the charges that is going to contribute is 8 into 10 to the power 15 per cubic centimeter. Assuming the mobility values are 1350 for electrons, and for holes it's 480. So the applied electric field is 100 volts per centimeter. Now you see we have an N-type material, so we can evaluate the electron and hole concentrations assuming thermal equilibrium, and we see that this majority of the charge carriers are coming from arsenic, right? So N is 8 into 10 to the power 15, and you can evaluate the hole concentration. And if you compare these two values are, this value is in magnitude is very small compared to that of electrons. So the majority of because of the difference in the magnitude between the two concentrations, the conductivity is primarily due to the negatively charged particles. Those are electrons. Okay, so in a sense, the conductivity is going to be of the material is going to be governed by the negatively charged particles only. Okay, this is a small quantity compared to the contribution of the negatively charged particles in the conductivity of the material. Okay, so we don't need to even consider for the holes, because of the very small concentration of holes in the N-type material. So if you just plug the values inside to find the conductivity of the material, just plug the values of the mobility of the electrons, the charge, and the concentration, which is given as such, This gives the conductivity as 1.73 ohm centimeter inverse, and the drift current density is then evaluated from the linear relationship of the from the given electric field. We have the conductivity, we have the electric field, so the current density is, you can see it's about few hundred amps per centimeter square, but still respectable. I mean, for a given applied E field, which is 100 volts per centimeter, 100 volt per centimeter E field tends to produce at room temperature a respectable current of few hundred sheet density or surface density. So this E field is enough to generate the current in an N-type semiconductor material having a value of 173 amps per centimeter square, a drift current density of 173 amps per centimeter square. So since this is an N-type material, the conductivity is essentially a function of electron concentration and mobility only, right? Conductivity, you can see, is dependent on the how much charge is being moved. This is the charge concentration, right? So it depends on the charge. This is the charge concentration between this term and the product of this term. These two terms are the this is the fundamental charge, and this is the concentration of the negatively charged particle. So this is how much coulombs you are moving, and this is the mobility. So these are all the factors which are affecting the conductivity of the N-type material. So the conductivity is essentially a function of the electron concentration and mobility only. So we may note that the current density of a few hundred amps per square centimeter can be generated in a semiconductor. So this drift current is a respectable current which can be generated by applying a small E field, right? Now, two factors that need to be mentioned concerning drift velocity and mobility are that the carrier drift velocities are a linear function of the applied electric field. Well, we know that because the velocities, or whether it is Hall, or if we consider this for the electrons, this is due to the applied electric field. So the drift velocities are, yes, they are linearly dependent on the applied electric field. You will have a velocity, you will have the charge is experiencing the force due to the applied electric field, and the drift velocity occurs due to the applied electric field, right? This is true for relatively small electric fields, and as I mentioned earlier, the electric field, if electric field is going on increasing, the carrier drift velocities will reach a maximum value of approximately 10 to the power 7 centimeters per second. That's the saturated, that's the maximum or saturated value of the drift velocity. So any further increase in electric field is not going to help to produce an increase in drift velocity, and this phenomena is known as a drift velocity saturation. Okay, it's not like you go on increasing the E field and the current generation goes on increasing. Well, it's not the case. Okay, it's going to get saturated. Now, the electron and hole mobility, which are constituting the and these values are given in previously example 1.3, those are constituting conductivity of the material. The mobility values are itself, they are actually a function of donor and acceptor impurity concentrations. So as the impurity concentration increases, actually the mobility decreases. So this secondary effect means that then the conductivity is not a linear function of impurity doping. So these two factors are important in the design of semiconductor devices. Well, yes, the conductivity does depend on the amount of the charge and the mobility of the free charge carriers in a N-type or P-type material. But if you go on increasing the impurity concentration, the mobility also is decreasing. Okay, so these are secondary effects which we are not going to much discuss in the design of these semiconductor devices, but they are taken up usually. These secondary effects are usually taken up in designing the of a semiconductor material for a certain conductivity and resistivity properties. Okay, so but we will not consider this in detail in this text. Okay, that's all for the drift current. We're going to continue with the diffusion current in the next video.